Bismillahirrahmanirrahim. Assalamualaikum. Good afternoon to all. This is our next topic on generic model under the advanced control subject. Basically, GMC or generic model control is a model-based control strategy. We can use linear and nonlinear models of the system to compute the control action directly in the formulation of the GMC, and also the response can be obtained by what we have two tuning parameters we call K1 and K2 inside the strategy itself, as you will see later. And basically, the JMC can directly use nonlinear models of process to determine the control action. So we don't need to linearize the nonlinear models that we have always been done for the linear control strategy classes. We linearize, but in this case, we do not have to linearize, which means the accuracy of the controller is much better, more reliable. However, it's limited to systems which are linear in control, or basically we call relative degree 1, which means linear in control, we'll see later, is that we are able to formulate in terms of u equals to something. If we cannot get u equals to something, then it will be difficult to implement. If the u is become a non-linear term and we cannot simplify it to get u equals something, then it's not basically linear in control and not relative degree 1, and we're not able to use it. These are some of the limitations. If not, you can use that GMC as long as we can be able to get the u to be formulated linearly. And of course, it requires process model and parameters. It's a model-based system strategy. As you look in the first introduction slide, this comes under the model-based strategies, other than the MPC. And this is the next one on GMC. And you need measurement of control variables, the one that you are control to the set point, the y. So of course, need to be able to measure that. In terms of the formulation, okay, a system x dot equals to function of x, u, and t. This is a general formulation for nonlinear systems. It can also for linear and nonlinear, but you will cover both. And the y is a function of x, the state variable, normal formulation. Y is the measurement where we need, or the control variable where we need to control. So in GMC, we want to get so that we can design the u so that it follows y dot equals to k1 epsilon plus integrate k2 epsilon dt in this form. Okay, k1, k2 I mentioned before, the tuning constants. E is y star minus y. Y star is normally the required value, which is set point in terms for control variable. So the error, and this is the formulation for the GMC system. The y dot, we'll have to analyze the model up there, and then we have to model itself. We're able to get the y. Okay. Basically, if you take from the model just now, yeah, the y dot will be given in terms of this one, and dhx over dx times dx over dt. Okay. Basically, this is the y dot dhx over dx times the dx dt. So you see just now, that's the function itself, the equation itself, function of x, u, and t. So the formulation of GMC is basically this one, k1 epsilon plus k2 epsilon equals to dh over dx times fx ut. So this is the formulation, and we need to basically get the u out so that we're able to formulate this in terms of u equals something. That's the most important thing. It should be the equation itself should be linear in control so that we can get the u out from the system. Okay. So again, if we put the fx ut in terms of this form, which is linear in control, because you can get the u in terms of the other parts or other terms, fx plus gxu. This is the form we need to have to be able to implement the GMC method. Okay, so if we have this, then we substitute back just now the k1 and e plus integrate k to e equals to the dhx dx times the equation itself, fx plus gxu, and most of the time this is 1, where the y itself is the state variable itself that we want to measure most of the time. So it comes, the GMC formulation simplifies to this from here, and from there we can formulate the U in terms of this equation. So this is the GMC formulation, is the GMC equation for control for the manipulated variable. This is the design of the method using GMC. All we need to know is the functions fx, gx, which is given from the equation itself, which is linear control. It can be non-linear, doesn't matter. And also, of course, the error we know from the measurement and the set point, and we need a bit of tuning for K1 and K2. So that's one more step that we need to know. Once we have the tuning, we're able to design the GMC much better in this case. Okay, so how to get the tuning? We can see from the next slide. Okay, from this equation we define K1 to zeta over tau and K2 to 1 over tau squared. Okay, and if you want to control an output of it, set point by 20 minutes. We choose and zeta to 10, and then from the graph we get the t over tau 0.25. So we substitute the t over tau, given that t is 120 minutes, so we're gonna get the tau 80 minutes, and we put into this equation. Okay, with zeta we decide from the graph which zeta we want. What's the behavior of the system we want. We'll see the next one. We get the zeta 10, we get the tau 80 minutes, substitute into this equation, we got K1 and K2. These are the tuning parameters. We may be able to what you call touch up or fine tune later. Not necessarily this is the best, but it's fine tune. But this is initially preliminary estimate of K1, K2 that we will use in our. Again, from this graph, we just now decide zeta equals to 10, so that we want a very quick value to the set point, and from there we pick up t over tau 0.25, and then we use the formulas just K1 and K2. Okay, for example, in this system where we have for variable x1 and for variable x2, yeah, for our first option is we want to control x1, variable x1, for y equals to x1. Okay, so if we formulate the GMC method, we'll get y dot equals x1 dot, which is given by this form equation. Okay, this is linear in control because the u can be formulated in this form. There's no non-linear terms that inside with respect to u that makes it not able to be formulated in this form. So it's a linear control method, so we can directly get u equals to y dot minus the whole form. Yeah, this is from the equation. All these are vector equations and dimensionless constants and so on that you see in vector. Okay, you can see the definition later in your reaction book. So this is the formulation, and y dot for GMC is given in this form. It's just we say, the tuning parameters with respect to the set point minus the actual value and so on. So we substitute inside here, and so we will get the U formulation for the GMC if we want to control the y equals the x1, y equals to x1. If we put another option that we like to control the x2 instead, we have the equation of x1 and x2 as state variables. But if we design the x2 and we get y dot equals x2, we will get this form, but then there's no u related to it. It's not about linear control, so there's no u, so we are not able to formulate the u, so we are not going to able to get the u to formulate using GMC. So in this case, we cannot apply the GMC. So GMC cannot be applied to control x2, but it can be only applied to control x1. Why? Because in the x1 equation, you get the u, and this linear control we can formulate in that form just now. But if you do x, y equals 2, we'll not be able to get it. So these are some of the limitations in using GMC. You have to decide the variables that will give linear in control in terms of u, the variables that we can measure, the variables that we can be able to formulate the u in a simple form, and we're able to tune the K1 and K2. So some of the small limitations of GMC. Otherwise, you can easily use it, and very easily use it for this controlling non-linear systems. Okay, sometimes state and parameters is also applied because we do not able to measure some of the variables, so we need to estimate it. Okay, so we estimate some using state and parameter estimators, put into GMC and then design it. Okay, some of the parameters inside it, not only the state variables, maybe the parameters we are not able, so we have to estimate using different types of to design it. So in summary, GMC is a simple non-linear control strategy that is much easier to understand and implement than other control techniques. In terms of non-linear, it's a simple one if we are able to get linear control. Able to get the U formula, we can simply easily implement that. Can be applied to non-linear process system because we don't need to linearize, just get the equation, put it into the formulation, and that's it. And it can be used with state and parameter estimators, to be able to control handle model mismatch or parameters that we are not able to estimate. We use estimators, and then we can. It's also limited. Is however limited to system which are linear in control. Linear, not linear system, non-linear, but the control side has to be linear control because we have to formulate the U to be able to get GMC as we have seen before. Okay, just some explanation if it can be applied in a vector, axiomatic vector involving high non-levity, sort of batch system. Okay, control the elements by practical and robust. So this sort of vectors which need practical, robust, good control algorithm without much overshoot. You can use GMC. We assume there are two parallel reactions and so on. The aim is to heat the vector content quickly from an initial temperature to desired temperature and control it at that temperature using GMC technique. So very precise technique is needed to bring it to that set point in a trajectory form. Normally this sort of batch vector system, which a batch vector, and we cool it from outside and heat exchange outside. You want to get temperature right into the set point without much overshoot, without much deviance, because it will spoil the contents. For example, pharmaceutical system, you cannot allow it to go to high temperature where it will destroy whatever pharmaceutical product that you want to produce. So those are things that we need advanced, precise control, including GMC and maybe the AI. Okay, and from the GLC algorithm, we know that is the y dot is a standard one. And this is the equation that we've seen just now in terms of fx ut, general one. This is the actual equation in terms of temperature vector and the heat release, heat transfer from jacket to temperature and so on. Standard exotomic vector balance, for in this case for the batch system, and we replace it by our normal nomenclature. The control input is U, the TJM itself, jacket temperature that we want to control, and the Y is the TRM, temperature of the vector. Okay, so this is all the Y's, and the others are the put it into the GMC formulation. This is what we're going to get. Just now was the general one. This is specific in terms of the set point, y star minus the actual value, y minus actual value. Okay, the formulation, and these are the standard CPR, heat transfer coefficient, and so on, minus this one. So this is the actual control input that we can implement. These are measured. These are some of the things we can get, or we have to estimate. Like Q heat release, will not be able to just get. We have to estimate. This is online. Different methods, and this is final form of the GMC formulation in terms of discrete. Normally it's in computer form, so it's algorithms of discrete time in terms of k at that time and so on. Just discretize the equation, and so implementation, it can be done, requires knowledge of some of the parameters which normally we know, assuming constant doesn't matter, but the measurements of the vector temperature and the jacket temperature and estimate of the QR heat release. As I said just now, the heat release can estimate using different methods. We can estimate using finite approximation method or Kalman filter using a simplified process model or rigorous process model. These are different methods where you estimator. We can also program it and put it in, or we can use simple equations to be able to estimate the Q if we need to estimate. If we have to just assume first, we can assume and then later estimate it. This is sort of the heat release model that we can use, a simple model to estimate the Q, and it's given in this form. This is one example of where we put in, and then we can use the Kalman filter, another standard method in the literature, to design the once you have the measured value, we can design to determine the Q release for the system. So, okay, this is so in terms of information flow sheet, you get a simulation or online, measure the TJMTFM, go to GMC controller, estimate the two-common filter for the Q, put into that formulation the equation, and get the TJ set point. The TJ set point is the U that we need to control. Okay, the temperature jacket that we need to control, we put at the set point because it's done control externally. So externally, the set point is for the heat exchanger. So this is what we want, and then it should follow roughly the TJ, and that is the actual U that is needed to be implemented into the vector to be able to control the vector to the profile. Here is some examples of experimental system that have been done in the papers and for I can't say clear, but this is the set point we want, and this is the actual. Initially, it's not able to control, it's out of control because it's not able to fit in, but slowly it sets into the control, follows the profile because of the initial estimates of Q that we are not able to get initially. So this is the sort of the temperature jacket cap that we want. So finally it follows the jacket temperature that we need to control it, and this is the Q measurements for the estimation. Okay, how far that we need to estimate to these actual results that we get, and to show that it can work experimentally, not only just simulation. Real world GMC also is very practical and can be implemented. Okay, thank you very much for your time.